Hi everyone, good day. Are you ready for another Math Venture with Teacher Rev? Let's start our statistics learning journey. Hi, so today we're going to talk about combination. What is combination? A combination is a selection of all or part of a set of objects without regard to the order in which the objects are selected. So, for example, suppose we have a set of three letters A, B, and C. We might ask how many ways we can select two letters from the set. So if we are going to do that, we have AB, we have AC, and we have BC. Each possible selection would be an example of a combination. Note that AB and BA are considered to be one combination because the order in which the object we are selecting does not matter. This is the key distinction between a combination and a permutation. When we talk about permutation, a combination focuses on the selection of objects without regard to the order in which they are selected. A permutation, in contrast, focuses on arrangement of objects with regard to the order in which they are arranged. So if we are going to get the permutation of the three letters taken two at a time, we can have AB, AC, BC. Also, AB is different from BA since the order is important in permutation. That's actually their distinction. But today we're going to focus on combination. Since we know the difference between combination and permutation, then we can say that the number of ways from a permutation of R elements from a total of n can be determined or equal to the combination of R elements out of a total n, ordering these R elements any one of R ways. That means, by the multiplication principle, the number of ways to form a permutation is equal to the number of ways to form the combination times R factorial. Using the formula for permutation, we have n factorial over quantity n minus R factorial is equal to the combination of R elements out of the total of n times R factorial. That means to get the combination formula, we simply need to multiply both sides by 1 over R factorial. That would mean we can cancel R factorial in this side, arriving with combination of R elements out of a total of n is equal to n factorial over quantity n minus R factorial times R factorial. That arrives us with this formula, that to compute the number of combinations, an R combination of elements of a set with n distinct elements is an unordered elements from the set. The number of R combinations of a set with n distinct elements is denoted by the given formula, which is the one that we derived, where n is a non-negative integer and R is an integer whose value lies from 0 till n. Now, best way to apply this is to use different examples. Let's have our first example. The figure shows a digital padlock. Suppose you forgot the code and you want to open it by guessing how many 4-digit combinations are there. Definitely, since given the illustration of the padlock, order is not important, so this is a combination problem, which follows that we are going to use the formula of n choose R is equal to n factorial over quantity n minus R factorial times R factorial. In this case, we have to identify first what's the n and what's the R. We know that we are going to form 4-digit combination, so R is 4. But we don't know what is n. Looking at the illustration, there are 8 numbers to choose from to form the 4-digit combination. Therefore, n is 8. Then, to find the number of 4-digit combinations that we can have out of the given, we have to find 8, choose 4, which is equal to 8 factorial over quantity 8 minus 4 factorial times 4 factorial, which is equal to 8 factorial over, since 8 minus 4 is 4, then we have 4 factorial times 4 factorial. Let's do this manually first. So what we can do is actually express 8 factorial in terms of 4 factorial. So we have 8 times 7 times 6 times 5 times 4 factorial over 4 factorial times, since there's already one 4 factorial, we can expand the other item as times 4 times 3 times 2 and times 1. In that case, we can cancel the common factors, and the common factors are 4 factorial. Again, any non-zero number divided by itself is equal to 1. That's why we put 1 there. We can cancel 4 and 8. That's 2 and 1. We can cancel 3 and 6. That's 2 and 1 as well. But we can still cancel 2 with any of the 2 there, but I prefer canceling that. So that's 1 and 1. So the denominator is already 1. That means we're left with the numerator of 2 times 7 times 5. And 2 times 7 times 5, let's use our calculator. That's 2 times 7 times 5. The answer is 70. Therefore, there are 70 ways to form 4-digit combination for us to be able to unlock. We can have 70 trials to unlock the digital padlock. Okay, so is there any other way of doing it? Actually, if your calculator contains the factorial notation, if you have a scientific calculator, we can set up from this part. We can actually use 8 since factorial notation in this scientific calculator is a shift function of x raised to -1. Then I click on shift, then click on x raised to -1 to show the factorial notation symbol over 4 shift factorial times 4 shift factorial as what is stipulated in this form. Then I can click on the equal sign and my answer is 7. It's the same answer that we have in the given example. Okay, that's just another way of doing it. Let's have another example. There are also examples such as this. This is something that's familiar. How many ways can 5 representatives be chosen from a class with 35 students? The 5 representatives that we're going to choose from will not be ranked nor placed in a position. That means this is a combination problem. What's the difference, or how will I make this problem a permutation problem? If I included that how many ways can 5 representatives be chosen from a class with 35 students such that the representatives will be assigned as president, vice president, secretary, treasurer, or ERO, then that problems when there's designation because there's particular order in which the students will be identified, then that becomes a permutation problem. But in this case, let's focus on our combination problem since we're asked to identify 5 representatives out of 35 students. Okay. Since it's a combination problem, we're going to use the formula n choose r is equal to n factorial over quantity n minus r factorial times r factorial. In this case, what's n and what's r? N is 35 because there are 35 students from which we will choose the 5 representative. That means r is 5. Following the formula, we have 35 choose 5 is equal to 35 factorial over 35 minus 5 factorial, quantity 35 minus 5 factorial times 5 factorial. Let's do this manually. So we have 35 factorial over, 30 factorial times 5 factorial. Then we can equals, let's write 35 in terms of 30 factorials, 35 factorial in terms of 30 factorial. So we have 35 times 34 times 33 times 32 times 31 times 30 factorial over 30 factorial times 5 times 4 times 3 times 2 times 1. Again, I'm going to expand the other factorial because there's only one way I can cancel the factorial. That is 30 factorial. That means this is 1 and this one. I can cancel 5 and 35. That's 7 and 1. 4 and 32. That's 8 and 1. 3 and 33. That's 11 and 1. And 2 and 34. That's 17 and 1. So I have 7 times 17 times 11 times 8 times 31 times 1. And the answer is, let me use my calculator, 7 times 17 times 11 times 8 times 31 times 1. It's okay. So I have 324,632. 324,632 ways that I can choose 5 representatives out of the 35 students in my class. How many different pairs of cards can be chosen from the 5 cards in a royal flush? This is an example of a royal flush. So the thing is, we're going to identify different pairs of cards. Definitely, since we're going to choose, order is not important, then this is a combination problem. Therefore, we're going to use the same formula. N factorial over quantity n minus r factorial times r factorial. But we have to identify what is N and what is R. We know that we are going to get pairs of cards. So if it's pairs of cards, definitely R will be 2. And we're going to choose it from 5 cards in a royal flush, therefore N is 5. To solve this problem, to identify the different pairs of cards that we can choose from the 5 cards in a royal flush, we can get 5 choose 2, which is 5 factorial over quantity 5 minus 2 factorial times 2 factorial, which is equal to 5 factorial over 3 factorial times 2 factorial. And that's equal to 5 times 4 times 3 factorial over 3 factorial times 2 times 1. I'm going to expand that. Okay, we can cancel 3 factorial. That means that's 1. We can cancel 2 and 4. That's 2 and 1. And we're left with 5 times 2, which is equal to how much? Exactly. There are 10 ways that we can identify pairs of cards, or that we can choose pairs of cards out of the 5 cards in a royal flush. Combination problems can also be applied to geometry. Let's analyze the problem first. How many segments can be formed from 5 points such that no 3 are collinear? Let's name these points first as A, B, C, D, and E. We know that a segment has 2 endpoints. Therefore, if we are going to form segments A and B, that's one segment. Can we say that segment AB is the same as segment BA? Yes. So that's counted as 1. We also have BC and CB, that's the same, so it's counted as 1 as well. Segment CD and DC is the same, so that's 1. Same with ED and DE, that's 1, because to form a segment, we can have that. Connect 2 points to have an endpoint. That's another 1. But we can also have other segments, such as segment BE, that's 1 point. Segment BD also, that's another. Segment AC, that's 1 more. Segment CE, that's another. Other than that, CE and EB and BE are the same, so it's there already. But I can connect A and D. That's another point. If I'm going to count all the segments, that would be 10. I have 10 segments, so I can form 10 segments out of the 5 points in the given. But notice that the 5 points, to be able to form a segment, you need 2 points out of the 5 points, correct? So definitely, we can use combination in this type of problem. How are we going to do that? We can actually get 5 choose 2. Why 5 choose 2? You have 5 non-collinear points. And you have to be able to form a segment, you need 2 out of these 5 items. We have 5 factorial over quantity 5 minus 2 factorial times 2 factorial. That will give me 5 factorial over 3 factorial times 2 factorial. I can actually write 5 factorial in terms of 3 factorial. So I have 5 times 4 times 3 factorial over 3 factorial times 2 factorial. I can cancel this because they are common factor. That's 1. I have to expand 2 factorial as 2 times 1. Therefore, I can cancel 4 and 2. That would leave me with 2 and 1. Then I have 5 times 2 and I have 10 segments. Is it the same with what I have from manually doing it? Yes, that's exactly the same. So this type of problem we can use combination. This had been a great learning adventure. So, see you next time on another Math Venture with Teacher Rev. Remember, don't stop until you're proud. Learning math takes time. Bye!